Okay, so let's kind of go through all aspects of the lab. So the first thing that you did was that you said, all right, here's a block, and we need to figure out a couple of things. First off, how much it weighs. There's two ways you can figure out how much something weighs. Take a Newton scale, hold up, that's what you did because you don't know what the mass is. Or if you know what the mass is, you take the mass in kilograms, multiply that by the gravitational acceleration. You not tell me it's mass times gravity, that makes no sense at all. It's mass times your gravitational acceleration. I'll even accept mass times g. Just don't tell me it's mass times gravity. And then that's going to get you your gravitational force, okay? So as the block is sitting there, if you're on a surface, you have Fg and you're going to have force normal. So if you're sitting on any kind of surface, those are the two forces that are always present, okay? Boom. So there's a couple of things that were important. Number one, in that beginning part where you're trying to figure out the value of the coefficient of friction, you figured out how much force it took to pull it at a constant velocity, okay? Let's say that was, I don't know, 1.20 newtons. Whatever force it took to pull it at a constant velocity. So here's what's important. The only reason that that force has to be there to keep it moving is because of friction. If you eliminate friction, you don't need the applied force to keep it moving. So get out of your minds right now that, oh, you always have to have a force to have motion. You don't. If there's no friction, or in a weirder situation, if you were in like deep space, and there's no effective gravitational field, you don't, inertia would just keep it moving, okay? But we're not. We're on Earth. We have friction. We have the electrostatic force. So whatever your applied force is whatever your frictional force is. So like for example, if you could take your car and you could measure how much force it took to pull your car at 40 miles per hour, that's how much frictional force there is working against your car, okay? Simple way. It's the easiest way to do that. So you need to draw a couple of diagrams relating to this situation. The first diagram on number 3 is that's what this is going to look like, okay? So if your applied force is 1.20, your frictional force is 1.20. If your block weighed negative 3.92 newtons, your normal force is going to be 3.92 newtons. So this first diagram should look like a big plus sign, okay? Drawn to scale, not a sketch. Drawn to scale. You're going to show me, hey, Mr. Burkamp, I let 1 centimeter equal a newton, or I let 2 newtons equal a centimeter. Whatever you did, that's what the first diagram is going to look like.
Is force friction negative or no?
Yes, typically you make the force friction negative. You can make it positive, but then your applied force would have to be negative. Okay? But typically the frictional force is defined as a negative value. Okay? So that's what diagram number 1 is going to look like. Then you're going to draw it tip to tail. Personally, I always draw my gravitational force first, then I do my force applied, then I do my force normal, and then I do my force friction. Okay? You should end up back at the origin because of the fact that you're at a constant velocity. There's no imbalanced force. Okay? And without an imbalanced force, you maintain a constant state of motion. That constant state of motion might be at rest, it might be at 5 meters per second, it might be at negative 12 meters per second. I don't know. But if all those forces drawn tip to tail, no matter how many there are, you end up back at the origin, you are going to be at a constant velocity. Okay? Got that one. So you're going to use the same scale here as you did on the first one. Okay? Don't switch up the scales. It's just, it doesn't make any sense at all. So however long this is however long your FG needs to be on the next diagram. Okay, if that makes sense. All right? Now, your graph, when you get down to number 5. So what you did is that you began to add weights to the block, and then you measured how much force it took to pull it, okay? So what I want you to draw on your scale is that you're gonna put force friction on this axis, and you're gonna put force normal on this axis. Now, but you're going, but Mr. Burkham, oh, this is bad. We didn't measure the force friction. You did by measuring what?
Force.
Yeah, you measured how much force it took to pull it at a constant velocity. Then by measuring that force applied, then you knew what the force friction was. Make sure on that normal force column that you add the weights together. Like on that first one, which was 0.2 kilograms, that's 1.96 newtons. You take 0.2 times 9.8, you get 1.96. You're gonna add that to the mass of the block, okay, or the weight of the block. So if your block weighs 3.90 newtons, that's 6, 18, 5.86. So your normal force is gonna be the weight of the 1.96 newtons plus the block. And then you're gonna then you took that off, and then you put on the 0.5, same process, okay? So when you look at this, you're gonna have points on this graph. Should be fairly linear, okay? Because the more normal force there is, the heavier it is, the more frictional force there is to make it that you have to overcome, right? So your line of best fit might go through 0, 0. It might, okay, but it might not. You just have to look at what the data gods tell you. So if you can get a better line of best fit without going through 0, 0, do it. Okay? If it happens to go through 0, 0, great. You just have to look at the data that you have. But here's what's most important. If you look at the instructions on number 5, I don't care what you've done for your line of best fit, but I want to see the points that you circled. I want to see those values written down, and then either on here or in this space on number 5, I want to see the calculation of slope. Okay? Just don't go, oh, here it is, it's a miracle. No, it's not. Okay? Show me that calculations, because everybody's slope is going to be a little bit different. Okay? Good up to that point. Okay. Now, let's talk about number 7. So on number 7, we're going to change up the situation. So up to this point, everything's been moving at a constant velocity, and we haven't had any accelerated motion. Okay? You pulled the block at a constant velocity. Up to this point, all of your velocity time graphs have been horizontal lines. So when you have a horizontal line in your velocity time graph, you don't have any acceleration because all of your forces add up to equal 0. We're not saying there aren't forces, we're just saying that all the forces add up to equal to 0. So your car is driving along. You're moving at 10 meters per second. Here's your car, right? Boom, moving on 10 meters per second. Whoa, gonna hit the brakes, okay? Gonna stop. So even though you don't have to, it's handy in this situation to look at your velocity time graph. Okay, you're starting off at 10 meters per second. What's your velocity time graph going to do when you hit the brakes? Hopefully go to 0. Okay, you don't have to find the time, but understand this is what's going to happen. You're going to go from 10 meters per second to 0. Are you going to accelerate? Is your acceleration going to be positive or negative?
Negative.
Someone has some negative acceleration. Now, the big red sign in the back that says F equals ma. Is mass ever a negative number?
Not possible.
No. So if I'm going to have negative acceleration, what has to be the sign of my force?
Negative force.
So I know when I get done, I have to have a negative force acting on this car. Okay? But then it's like, oh man, how do I find the force? Curse it. But you know that mu times force normal, the absolute value of that equals force friction. Cool. So I gave you mu, 0.7. There's a couple of things to remember about mu. It's never negative, it's a scalar quantity, it never has any units, and it's rarely bigger than 1, okay, like 1.05. If you ever get a mu of like 7, you have done something horribly wrong, okay? So, I gave you mu. Now, that's the coefficient of friction. I know that that's not the frictional force, because if it was the frictional force, which it's not, but if it was the frictional force, what units would I have put on the end of it?
Newtons.
Newtons. I didn't. I just say, here's the coefficient of friction is 0.7. If I wanted it to be the frictional force, I would tell you, hey, the frictional force is 0.7 newtons. Okay? See the difference between the two. But can we use it to find the force friction? Absolutely. So now we know that that's 0.70. Force normal on a flat surface is the same as your weight, which is just mg. Do not worry about making any of this negative at this point, because everything's an absolute value. So you're going to take the 1,000 kilograms times 9.8 meters per second squared times 0.7, okay? You should get an answer around 7,000, okay? So what you need to decide then, because out of this, it's always a positive number because it's an absolute value. So what you need to decide in the context of the problem, does it make sense to make the force friction a negative value? Joe B, you nod your head yes. Why? And the velocity is positive, okay? The car is going in a positive direction, okay? The car is going in a positive direction. If you want to stop the car, are you going to push it in the same direction that it's going? No, because that's only going to make it go faster. So, mathematically, your force friction will always be a positive number. You just have to decide, does it make sense to make it positive or negative? Okay? Good with that one. So your answer to number 7 should be around 7,000-ish. Okay? When you get done. Okay? So the only difference between 7 and 8 is that I've given you a bigger coefficient of friction. So here's the story. Let's say I'm going to give you 2 velocity time graphs. One's very shallow, one's much steeper. They both have the same initial velocity. Which one is going to have the bigger acceleration? Line 1 or line 2? Line 1. It's a steeper line, right? So line 1 has a bigger acceleration. So which one has more force acting on it? Line 1 or line 2? Line 1, because force equals mass times acceleration. True? Now here's a little algebraic voodoo that you can do. Okay, just a little bit. If you look at mu equaling force friction over force normal. Okay, this is just a simple, it's kind of a cool way to look at this. Well, force friction can equal mass times acceleration, which is what we're going to do here on number 9. Okay? So force friction can also be written as mass times acceleration. Well, force normal, which is the same as your gravitational pull, is mg. So if you look at it this way, the masses cancel out. Mu can also be viewed as a ratio of accelerations. So when I take this cart and I give it a push, okay, it slows down a little bit. So if I knew what the acceleration of the cart was, I wouldn't need the mass. I could just take the acceleration of the cart and divide it by 9.8 meters per second squared. Okay, speaking of number 9, so your acceleration should be around negative 6 meters per second squared, because if that answer is wrong, everything is going to be wrong. So that first acceleration on number 9 should be around negative 6. Do not make the force friction calculation difficult. You know F equals ma. You just found the acceleration of the car. You have the number. You know what the mass of the car is. You have that number. All you have to do is multiply the mass times the acceleration to get the force friction. Do not make that difficult, okay? It's just mass times acceleration, that's it. Now, to get to mu, here's what you could do. One option, which I just showed you, is you could take that acceleration that you just found and divide it by 9.8 meters per second squared. That's option number one. But wait, there's more. Option number two, you go, oh, Mr. Burkamp, I love forces. I want to be a Jedi. Good for you. So your other option is that you take the force friction that you just found. You already have the number. Okay, it's around negative 5,000. And then you take the mass and multiply that by 9.8 meters per second squared. And then you get the normal force. And then you do the whole thing, okay? You do force over force. That's an option. Or you do A over G. I don't care. But that coefficient of friction on number 9 should be around 0.5, okay? It's an ish, but it's around 0.5, okay? Which should make sense. It's like, oh yeah, it's got to be less than 1. Cool, got it. Okay, when you get to the Lord of the Rings question, so keep in mind what happened. You had vector A, which was 0 degrees, and then you had another one over here, B, and you had another one over here, C, okay? So, A is the one that's at 0 degrees. That's the one that you cannot change the angle, because that one was set in stone. So, here's the idea behind this. This is a three-way tug of war. B is pulling this way to balance out the effect of A and C. C is balancing out the effect of A and B. So each single vector is balancing out the effect of the other two. So if I didn't do this because it would have been really boring, what if I, due to budget cuts, we can only have 2 strings? We can only have 2 forces, but we want to be in equilibrium. Why would that be boring? Yeah, they'd have to be the same. The only way 2 strings can be in equilibrium is if you have the same amount of force pulling on both sides. Now, here's an interesting thought. It's like, oh, further budget cuts. We're down to 1 string. That's all we got. It's like, what happened to your tables? I don't know. We only have 1 string. Can you get more? No. Is it possible for 1 string to be in equilibrium? No, because it's going to go in that direction. So the same thing is going to be true of forces. If you only have 1 force acting on any object and 1 force only, what does the object have to do? It has to accelerate, okay? If I let go of this ball, what's the only force acting on it? Guess what? What does it have to do? Accelerate, because that's the only force acting on it. There's nothing else. Now, if I hold it up, now how many forces are acting on it?
2.
Now I can make a 2-force system be in equilibrium, but I can't make a 1-force system be in equilibrium. Okay? All right. Your diagrams. You should have, count them, 2 diagrams for the Lord of the Rings. Well, one is going to be a free body diagram that's going to look something like this. Okay? And it's going to be based off of the forces, not the masses. Why don't we ever draw masses as a vector diagram? Is mass a vector quantity or a scalar quantity? Yeah, it's just a mass. You can't give mass a direction. It's like, what do you weigh? 120 pounds north. Really? Weird. Okay? But this is why you have to have the forces. So the first diagram is going to look kind of like a starfish. The second diagram, I would draw vector A first, and then you're going to draw vector B, and then you're going to draw vector C. Hopefully you end up something close to back to the origin. Okay, you might be off by a little bit, draw it however you get it. Now, if you end up like out here, something has gone horribly wrong. Okay? All right, any questions at all beyond that? Hopefully I kind of went over everything. Okay? When you staple it, where are you gonna put your diagrams? On the front or on the back? Let's go with the back. Stapling, it's a skill. We haven't talked about this for a while, so I want to revisit that idea. Okay, all right.
Did you do it again?
No, I didn't.
Oh,
So,
that was strange. It acts as a torment.
do I start from the?
No, it's strawberries. It's okay.
Yeah, tip the tail.
None of the back there.
This is what you just did.
I didn't get the mixed part, but I've got everything before that except for this and number 3. Oh wait, I'm just coming in here. What's number 3 on 11?
Oh, yeah.
Or like, which one am I missing? Because I have find the absolute value of. Are you kidding?
Yeah, I literally was crushing out.
That's the only one I did know.
No, because yeah, you're not missing negative.
So the angle that you should get should be vector B. So for us, that's 85 degrees.
Can I turn this in at the end of class?
Just about.
Okay. My vectors were so messed up.
We don't have round. 2,000 kilograms times 9.8.
Just carried around a giant.
Oh, no, that would be 1,000. 1,000, so then it's 9,800
still
exactly
on.
down. So that means the force normal is also 98.
Yeah.
So every time I walk by, it's
The force,
Yeah.
force bridge by doing.
It's supposed to be over.
Times.
oh, it's definitely.
I didn't eat any of my lunch because I was just working on my assignment. And then every time I asked another question, I looked at me like I was stupid. Which I am, but it's still hurt. Yeah, you can look for on himself. Wait, what is that? No, what's it? Oh, strawberry juice.
I was like,
Be
your
good for a
sandwich?
defense season. And maybe
Your sandwich.
Just look at it, it's like all that red, and it's like,
Oh yeah, she had a jello
it's
sandwich.
not.
and she can't stand it.
It's her Mormon
Yeah,
family.
yeah, forces.
Her Mormon family. makes
Okay,
it.
are we still rolling, Mara?
Yes.
Okay.
Yeah, we never stopped.
Okay, sounds good, all right. So what we're gonna do is like 3 different examples of how Newton's laws play out and how you can actually use this. So the first thing that we're gonna do is that we're gonna use this cart, fan cart, which we've used before. And I'm gonna turn it on, I'm gonna let go of it, and it's gonna begin to accelerate, right? So what I want to do is determine 3 things. The mass of the cart, the acceleration of the cart, and the force acting on the cart. And then when I get those numbers, I want to see if this thing could fly, okay? That's what I want to see. So I want to find the mass, the acceleration, the force, and then see if it can fly, okay? So let's talk about mass. So how could I find the mass of the cart?
Newtonometer.
Take a scale. I happen to have one. And it measures in newtons, oddly enough, being in a physics classroom. So I hook this up, and it weighs 4.31 newtons. Okay? So it weighs 4.31 newtons. So how can I take the fact that it weighs 4.31 newtons and roll that into mass? Yes, Ms. Vogel.
divide by 9.
Well, what does FG equal? MG, right?
Yeah.
Right? So if this is 4.31 newtons, I divide that by 9.8 meters per second squared, I can get mass. So somebody take 4.31 and divide that by 9.8.
0.440 kilograms.
Point what?
440 kilograms.
Kilogram. If I go to the moon, what's going to happen to the weight of the cart? It's going to be less. What's going to happen to the mass of the cart on the moon? Because mass is a measure of stuff. Okay? You can also view mass as a measure of inertia. Inertia is a resistance to a change in velocity. So, if you don't have very much mass, that means you don't have very much stuff to move. The more stuff you have to move, the more force it takes. Okay? Okay, so I got the mass part done. So, I happen to have a meter stick. And I happen to have popcorn with a stopwatch. So what can I do?
Measure distance and time.
Measure distance and time. Okay, we can go old school. So if I set this here, and I'll put the back wheels at 0, I'm going to let it roll until the back wheels cross the 60 centimeter mark. Okay, so I'll tell you when to stop it. Okay, so we're going to get it going up to full speed. Okay, you ready? 3, 2, 1, go. Stop.
2.5.
Exactly?
Yeah.
2.50.
Yes.
So the distance traveled was 0.60 meters, and it took 2.50 seconds. Could I find the velocity by taking 0.6 meters and dividing it by 2.5 seconds?
No.
No, why not? What kind of velocity do I not have?
Constant.
So help me, okay? If you see any accelerated motion, what do you not do? Distance divided by time. Okay. I can't take meters and divide it by seconds. But what else do I know?
Initial,
Huh?
the initial velocity,
The initial velocity, which is what?
0.
Oh, the initial velocity is 0. That's kind of cool, right? So, what equation relates distance, acceleration, time, and initial velocity?
D equals V naught T plus 1/2 AT squared.
Okay? Distance equals 1/2 AT squared plus V naught time. We're clever. What's our initial velocity? 0. So 2D over T squared gives me my acceleration. Okay? Cool. Got it. Grand. So somebody take 2 times 0.6 meters and divide that by 2.5 seconds squared.
0.192 meters per second squared.
What'd you get? 0. What?
192.
Meters per second squared. Now, that's in sharp contrast to the acceleration due to gravity, which is 9.8. Okay? So it's accelerating, but it's just a slow rate of acceleration. Okay? We're still accelerating, it's just not breakneck speed. This is even slower than acceleration on the moon. Acceleration, free fall acceleration on the moon is like 1.7 meters per second squared. So this is like really watching this thing in slow motion. So at this point I have the mass and I have the acceleration. So what can I find?
Force.
Oh, now I can find the force. Because oddly enough, force equals mass times acceleration. That's kind of cool. So it said the mass was what? 0.440. And the acceleration we just found to be 0.192 meters per second squared. So somebody, Jackson, take 0.44 times 0.192. That's a 2.
8.45 times 10 to the negative second newtons.
Is that much of a force?
No, not at all.
Not much of a force. So here's the question. Could it fly? Why not? It's got a force. Come on. The propeller spins. Look, it's making it go. I can feel it, right? It's even enough to kind of give me that wind-blowing model look.
Gravity is stronger than the force making it move.
How do you know it's not strong? What's bigger?
Gravity.
Yeah, the gravitational force is bigger than the force from the propeller. So if I do this, I turn it on and let go of it, what's not going to happen?
It's not gonna go up.
Yeah, I don't have to worry about, I let go, like, oh, God, okay? No, if I let go of it, it's gonna fall. Now, is it gonna fall at the same, at 9.8 meters per second squared? No, it won't quite fall at 9.8 because we do have a little bit of upward force, but certainly not enough that, I turn this on, it's like, whoa, stop, okay? Not gonna happen. All right, so speaking of accelerations, we do another one. So, Mara, I'm gonna need you to stand up. We need to look at the back of the room now, or in the middle, I should say.
Wait, I stand up?
Yeah.
So,
That's fun.
we're going to make a small.
Not consent to be on camera.
Is it working? Kayla, fix it.
So you can put it up a little bit.
And that
Hold it.
vaporize.
You got that.
Huh?
Are you on broadcast? Huh?
Okay.
Are you on broadcast? No.
So, at this point, from a chemistry perspective, we're going to start a redox reaction, okay? So, for those of you that have had Chem 1, which I'm guessing is the vast majority of you, this is going to be a combustion reaction between a hydrocarbon and oxygen. What do you get out of any combustion between a hydrocarbon and oxygen? Two things. Water and carbon dioxide. What are you all exhaling right now? Carbon dioxide and what? Water. You do. You don't believe me when it's cold outside. What do? You act like you're smoking. You think you're cool. Look, I'm smoking, right? Ever do that at the bus stop? Oh, I'm cool. Okay? So, but that's just the water vapor that you're breathing out condensing. Because you all were nothing but redox reactions. Okay? No, it's true. You all are just a very small scale. Just like, oh, I hear explosions inside of me. No, that's not what you feel. That's something else. You're on something. Okay? So, sure. So, this is just basically what's happening on a cellular level, but happening very, very rapidly. So, hold on. I need some air.
I don't have a schedule anymore.
Lights on, lights off.
I will actually cut it on.
Off.
You know I can hear you, right? Yeah.
Oh, it is.
Thanks. Not my birthday.
The camera can actually see the
Okay.
reaction. Oh, am I in it now?
You were. You were.
I can't move.
For like a second.
Tiny, move closer.
Okay, ready? Just
Yeah.
tap them on. There we go. Okay, ready? Okay. Oh, and then it's the boomerang. It comes back. Okay. Now, if you feel the side of this, warm, okay? So not only do you get carbon dioxide and water vapor out of this, you also get heat. Which is why you feel warm, okay? It's an exothermic reaction. If it was an endothermic reaction, the container would feel cold, okay? But it's exothermic. So if you look at it from like a roller coaster perspective, the oxygen and methyl alcohol was like at the top of the roller coaster. It had a lot of potential energy. So when I put the match in there, that was like pushing the roller coaster over the top of the hill. And if you've been on a roller coaster going down, people go, ah! They do this, okay? The flames and the heat and everything else was all of the chihuahuas being rearranged rearranged, and the chihuahuas going, "Yee-yee-yee-yee!" Okay? So you just saw the results of rearranged chihuahuas, okay? And it was cool. Now, did the rocket accelerate?
Yes.
Admittedly it did. Why?
Change velocities.
Well, we know that, we have to change the velocity. But what was the mechanism that made it move in that direction? Oh yeah, that's what started it.
Force of,
But why did it go in that direction?
Because all of the air is coming out that way.
So the arrow's coming out this way,
Equal and opposite reactions.
thrust.
okay?
Oh, man. that doesn't-
Hold on.
There's a little gap.
Hold on. Sarah. Let's say that we'll focus on one of the carbon dioxide molecules that were produced. So Chucky, the carbon dioxide molecule was produced, out of the byproduct of this. So Chucky got pushed out the back. Is Chucky pushing out the back what's making the force to make this go forward?
The air being pulled in.
Oh, no, trust me, there was nothing but air going out of this thing. So here's my question. When Chucky leaves, Chuck runs into air that's out here. Is this interaction out here between Chuck, which is being ejected at a very high velocity, hitting the existing atmosphere, is that what is creating the force to make it go forward? Everybody cool with that idea? Okay, so it's the gas here hitting particles out here that make this go forward. Let's think about this. This is a problem if you're right. So what do you know about space? Is there an atmosphere or is it a vacuum?
Wait, so Star Wars is impossible.
No.
Oh, my God.
Space is a vacuum, right? Everybody has this romanticized version of space. Oh, space will kill you, okay? Quickly. It's a vacuum. You have highly ionized particles from the sun that are going to bombard you and jack up your DNA, okay? No, space is not cool. Space will kill you. And we exist because we have, if the earth was the size of an apple, and you cut an apple in half, and you see that red layer of peel, that's the scale of our atmosphere. So we live because of an apple peel thickness of air that surrounds our rock. Okay, that's it. That's the only reason that we're here. It's because of that relative size of the rock. So space is a vacuum. So if the interaction came from these particles hitting particles out here, then we could never use rockets in space because it's a vacuum. So when the particles get ejected into space and it's a vacuum, there's nothing for them to push against. Now, let's just think this through. You say it's Chucky hitting always the oxygen molecule that's out here. So let's just look at that interaction. So here comes Chucky, right? Chucky, the carbon dioxide molecule, just got made. He's going, cool, I'm carbon dioxide. I was just oxygen before, but now I'm carbon dioxide. I'm really excited. And he wants to tell all his friends. So he runs into the oxygen molecule. So think about this. So here's Chucky. Chucky's going this way. He runs into the oxygen molecule. Okay? So what are some things that could happen between Chucky and the oxygen molecule?
Equal and opposite.
Yeah, so Chucky could bounce back. Okay, so which is incredibly small chances because they're small spherical things. But let's just say on the odd chance that Chucky does get bounced back. Then Chucky would have to go against the other Chuckies that are coming out and interact with them, which seems odd because as soon as I lit this thing, what did it do? Bam, it took off going that way. So everybody else is going, hey, good for you, Chuck, we're out of here. Okay? Because they've all left the building. They're out of here. So what's happening here, not the story. What's happening here is not, any interaction back here is not the story. Because if you had to have particles for it to push against, we could not use rockets in the vacuum of space. because there will be nothing for it to push against. Now let's think about this for just a second. We rearranged the chihuahuas, everybody got excited, woo, it's party. Heat was given off, yelling, screaming, we saw flames, it was cool. Do you think there was also particles slamming against the sides of the container?
Yes.
But why didn't it accelerate sideways?
Because there's a wheel around. The only way for it to escape is back.
Oh, no. Okay, were particles hitting this side?
Yes.
Yes. It's got a good beat to it. Okay, so particles were hitting this side. What were particles doing on this side? Hitting it. Do you think they had the same number of collisions?
Yes.
Yes. Same number of collisions. That's why we didn't accelerate sideways. Did you have a bunch of collisions against the front of it?
Yes.
In the jungle. Okay. So, you had a bunch of collisions hitting here. Do you think you had a bunch of collisions hitting back here? Yes. Now this part. You had collisions hitting here. What did you not have? Oh, you didn't have collisions here. So you had more collisions on the front than you did on the back. So what actually drove it going forward? Collisions with the front. You had an imbalanced number of collisions on the front. What happens back here had nothing to do with it. Okay? So if I put a blast shield right here, would that have made any difference? Absolutely no difference at all. Would not have made any difference. Because the particles would have hit, they would have hit the blast shield, and then they would have had to turn around, come back here, somehow interact with the, no. It's all happening in front. Okay? Got it? Good. Great. Okay, turn the lights back on. Jackson, how are you swinging the sledgehammer?
Huh?
How are you swinging the sledgehammer?
I can swing a sledgehammer.
Okay, good. I'm gonna put my light on.
Alright, cool.
Please give me a sledgehammer.
Okay. So, the last and final example of Newton's laws, which has become a fan favorite over the years, is that I am going to trust my life in Jackson's hands. And there's that bed of nails back there. So, I'm going to lay on the bed of nails, like so. We're going to put the concrete block on top of me, on my chest. Jackson is going to take a sledgehammer, okay, and smash the block while it's on my chest, okay? I tell most people this is like, are you just an idiot? Really? You have a bed of nails, a sledgehammer, and a teenager. What could possibly go wrong? So, but let's look at it from Newton's three laws of motion, right? First law of inertia, things don't want to accelerate. F equals ma, the big red sign. Third law says for every action, there is a reaction, okay? So, we're going to define down as being negative and up as being positive. It's arbitrary, but this is what we're going to do. So Jackson's going to come down and he's going to supply a negative force to me. Okay? So by Newton's third law, what has to happen between the block and me? What has to happen?
Acceleration.
No. Just in terms of forces. Newton's third law. For every force there is. So if Jackson supplies a negative force to me, what has to happen? There has to be an equal and opposite positive force pointing upward. Good. Now, this is going to sound odd unless you're in a physics classroom. When Jackson hits the sledgehammer, or when the sledgehammer hits the block, do I want the sledgehammer to accelerate?
Yes.
Yes.
Oh,
Yes. The alternative is that it maintains a constant velocity. If the sledgehammer maintains a constant velocity, somebody called Nurse Dana, okay, ever come down with ice chips and crackers. I want it to accelerate, but what do I want that acceleration to do?
Be positive.
I want it to be a positive value. I want that acceleration to make the sledgehammer slow down, okay? Am I going to accelerate?
Hopefully not.
A little bit, okay? Now, do I want a big acceleration? No, big acceleration's bad, okay? But now you look at this in terms of inertia. So the forces are going to be equal and opposite, right? So the sledgehammer has with part of Jackson, has a relatively small mass. So with a relatively small mass, hopefully it has a pretty big positive acceleration, okay? I want that sledgehammer to slow down. Now, the block, my chest, me, we have more mass. So hopefully we have a smaller acceleration. Notice that the laws are not, the accelerations are equal and opposite. If the accelerations are equal and opposite, I am not going to do that. Bad things are going to happen, okay? I'm not going to do it. I'll do it because forces are equal and opposite, not because accelerations are equal and opposite. So hopefully, on a velocity time graph, Jackson's going to hit with some negative velocity. What do I want that graph to do? I would at least go to 0, okay? Because if it does this, bad. If it does this, worse.
You didn't need your spleen, right?
I've got a couple extras. So, okay. So if you want to have your cameras and videotape it in case something goes bad, right? So,
Hey, Birkin.
what?
Does this have to be plugged in?
No.
Oh, thanks. I feel so much better.
Okay. Well,
Yeah.
Well, we got like first class seats.